like a sink term, but it's just as a variation of time. If you have a steady state, you have to respect that.
That's just concentration of mass, and the left term is like accumulation.
Correct, correct. So this is the accumulation term, and this is continuity. Okay, so what do we do with this now? This is what we found over there, right? So we're just going to write that out. Now variation of amount of fluid as a function of time is going to be all of this times density of the fluid. So alpha variation of volumetric strain, I'm just going to write here 1 over the Biot modulus dp, and I think that's it. That's it? Yeah, I think so, right? That's it. And here, now, I'm going to assume Darcy. And if I assume Darcy, what is going to be Q? Negative K divided viscosity times now the gradient of delta P. I have assumed not only Darcy, but I have assumed an isotropic solid, an isotropic permeability. That's why I can get this K out there. So let's see. Then this is going to be equal to 0. And if I continue working in these equations, if I assume, well, I don't have to assume anything. Look, I can divide by the density of the fluid is in this term, is in that term. So that's going to go to 0. Now I'm going to assume that this alpha remains constant with time. So I can take the derivative inside this term. Wait. It should be a second derivative. What? Because it's already there, right?
Yes.
Very well, thank you.
The other thing is that's divergence, yeah. So shouldn't it be the del dot? That's a divergence. That's a dot.
There was a dot there, no? No.
You need to put in the other one too.
Here, right?
Yeah.
So
These gradient
because we have a vector, we have a vector there.
So if we assume that k and mu are constant, so it's going to be minus k over.
So yes.
Laplacian.
So we're getting there. We're getting there, and then this is going to be plus 1 over m. Now dp dt, and now I'm going to assume that this is homogeneous solid, so I can take the k outside the gradient, and this is going to be just Laplacian of p equal to 0. And finally, I'd like to write this equation of variation of p as a function of time. And this is going to be equal to k Biot modulus divided viscosity Laplacian of p minus, right? Yes, minus alpha Biot modulus variation of volumetric strain as function of time. And what we just derived is the diffusivity equation coupled with poroelasticity. Probably you were familiar with the diffusivity equation just as a function of pressures. But notice that now we have an additional term. This is the term of the coupling with the deformation of the porous solid. The equation without this and considering compressibility over here and porosity is sort of a loose coupling or a one-way coupling because it tells you that pressures are going to depend on that compressibility, but it doesn't bring the deformation of the solid. With this equation, we could also tell that if you compress the solid under undrained conditions, you can cause an increment of pore pressure, something that you didn't have before. But now we have it. Yes, Preston.
So I guess here you're assuming that the solid velocity is zero. Because I guess for Darcy's is relative to the solid. So
Yeah.
the mass conservation equation, it would actually be the density of the fluid times, I guess the Q up there has to be a relative flux, or up even more, if you're pulling in Darcy.
So yeah, the solid is not moving anywhere. It's just the fluid. The one is well. I mean, it's not. It's deforming, but it's not moving in the grid. Well, there is displacement, but there is no flow of solid.
We're assuming small strains.
And we're assuming small strain as well of the solid, but there is fluid flow, right? So now we have this equation, and we're going to use this equation, which is the full equation of poroelasticity, in order to solve 3 problems of undrained loading. And we're going to discuss that on Tuesday. Okay? All right, guys. So I'll see you on Tuesday. Have a great weekend.
Are we going to have midterm next week?
Yes, we have a midterm on Thursday. Okay? In class.